Few words about Adshir. Adshir is a small company, a young company, founded in 2014, 6 years ago. We are making, developing, and commercializing real-time, low-power ray tracing software based on software. The name of the product is LocalRay. I'm going to repeat several times. Markets, of course, mobile gaming, AR, VR, and we are located in Tel Aviv, Israel. Okay, as John Petty said, ray tracing is a historical thing. It has a long history. Some people say even going back to the 16th century, when artists were rendering the models to create a realistic drawing. So this is what is ray tracing all about, to make it realistic. I can say a small story. In the beginning of 90s, I was a postdoc in the US in SUNY Stony Brook in New York. And we have a visitor, a faculty candidate. He was the first, it was just the beginning of ray tracing. And he showed us, he gave a presentation, he showed us a very nice picture, a beautiful image, never seen before. And he said, this is ray tracing. And in 1-2 years, it's gonna be a mainstream of graphics. This was about 30 years ago. And my question was, okay, how long did it take you to create this picture? He said, 3 weeks on silicon graphics, on a big silicon graphics system. So it's very complex. That's why it took about 20 more years to see the first movie created by ray tracing. It was Avatar. And just to show the complexity of the application, it was created on a farm, computer farm of 40,000 processors, and it took in average 40 hours per one single frame. So this is very complicated. So this is how ray tracing was and is done, ray tracing of cinema, of the films. Now, in order to have ray tracing for games, this is a completely different story because games are real time. So what was done, a new ray tracing was developed. This is hybrid ray tracing. Now, in hybrid ray tracing, and this is what today everybody which is doing real-time ray tracing is using hybrid ray tracing. So what is hybrid ray tracing? This is rasterization together with ray tracing, enabling real-time and a nice photorealism approaching the quality of offline path tracing. The principle is that usually the raster rendering generates the primary rays, and then the rest is done, the secondary rays, the bouncing rays, are taken by ray tracing to create the special effects. Not all the objects are taken for ray tracing, only some of them. And the amount of objects depends on the trade-off between the photorealism, and the frames per second. Let's see an example. This is a scene. We're going to use this scene for hybrid ray tracing. You see, this is a neighborhood, a city neighborhood. You see down there a yellow car. So now this is inside the environment, and everything which is in green is going to be ray traced. So you see that most of the scene it will be rasterized, but only the green ones will be ray traced. For example, the car. But when you ray trace the car, you need to you need the whole scene to be reflected in the car. So this is just the car, but the entire scene is used for reflections. Now, this is in the scene, the same car, the same taxi, ray traced. So you see the quality, this is a ray tracing quality, this is not raster quality. The building behind is rasterized. The taxi is ray traced, and also the Spider-Man. Let's see the animation, which is part of ray tracing, and we will see an animated ray tracing in the same scene. So let's look at this. This is raster, this is ray tracing. This is raster. Okay. So let's see what's the challenge in traditional ray tracing. There are 2 points, 2 challenges, 2 hurdles of ray tracing. One is accelerating structure. Accelerating structure is needed for ray triangle intersection. This is a very big data structure. It is traversed by every single ray to find the polygon which for the hit. The point is that when the scene changes, you have to reconstruct this accelerating structure. This is a kind of static data. Now, the meaning is that reconstructing such a data takes a lot of time. So this is exactly a thing that controversies with animation. Animation actually is a change of a scene. Now, if every change of a scene must be followed by rebuild of the accelerating structure, you cannot animate. That's the problem. So this is hindering of the animation. So we have heavy traversal, and animation is very, very difficult. Now, another problem is incoherence of rays. You see this small picture, there are primary rays, the black ones are primary rays, and when these primary rays hit an object which is not smooth, what you get is bouncing to all directions. So you cannot keep the rays together. So the meaning is that it's impossible to parallelize and optimize the rays because they are not coherent. And each ray has to be accessed individually in the memory. So you cannot use cache memory. These are the two problems of ray tracing, two challenges. Now, our technology, which is called LocalRay, we managed to reduce the complexity of ray tracing. So first of all, the proprietary dynamic accelerating structure, DAS, we call it DAS. This is a different accelerating structure. This is a dynamic one with a reduced complexity. Traversals are much faster. We do not reconstruct accelerating structures. You don't have to reconstruct because you update them in a local way. And the second point is coherent secondary rays. You know, secondary rays is the most important in hybrid ray tracing because the primary rays are done by rasterization. And the secondary rays must be coherent in order to make them in parallel, high performance, and optimized for cache memory. And that's exactly what we get. We will talk about it later more. So the advantages of this technology is reduced complexity, no rebuild of accelerating structures, software solution. The solution is software. We do not need hardware. We do not need accelerating hardware. The performance is high, low cost. Because of software solution, the cost is low and the power is low. Now, we can use any GPU. Because this is a software solution, any GPU can be used. Starting with 2 watts, which is a small GPU for mobiles, up to the biggest GPU. So this is off-the-shelf GPU, any GPU. And here I would like to show the correctness of the technology. On the right, you see LocalRay, a character rendered by LocalRay. Hybrid. On the small, you see V-Ray. V-Ray is a classic ray tracing. Of course, on the right is real time. On the left is not real time. Takes much more time. But you see, there's a change in colors because there are 2 different graphics systems. So they're using different materials. So the color is slightly different, but altogether is the same. So LocalRay is designed for mobile devices. The target of LocalRay is integrated GPU, which is this GPU of smartphones, low power and low cost. The integrated GPUs in smartphones, they are different from the discrete GPUs that are used in PCs. Now, remember that ray tracing is extremely memory intensive. It uses a lot of memory. So integrated GPU, unlike discrete GPU, do not have their own video memory, which is a great difference, big difference. If discrete GPU, the big GPU, has a big bandwidth, about 264 gigabytes per second of bandwidth, to its own video memory, integrated GPU can only have part of it, about as a 10% of the memory bandwidth, and the RAM, the memory, is shared with the CPU. So not only it can take only a small part of memory, but it has to share the memory with the CPU, and the CPU has a priority. So this bandwidth actually limits the integrated GPU. So integrated GPU is considered as not doable, it's not capable for ray tracing. Now, how do we enable integrated GPU? Okay. As I said before, we have a way to make the secondary rays coherent. Okay, so we are using coherency, which makes the integrated GPU capable to work with ray tracing. We are taking multiple rays of the rendering, and we put it together in the packet, processing packet. The same way this is done for primary rays in regular ray tracing. Now this processing in packets improves the performance, lowers the traversal cost, lowers the power, and lowers the memory bandwidth. This lowering, the reduction of memory bandwidth, enables integrated GPU of smartphones to ray tracing. This is the secret. So what are the advantages? Our advantages for mobile devices. So as I said before, we have reduced memory access and we have reduced power. Now, these two enable the next. We enable integrated GPU, as I said before. We enable low power consumption. Our consumption is less than 1% of NVIDIA RTX consumption. NVIDIA RTX consumption is about 250 watts. We can run on a mobile ray tracing with about 2 watts, 3 watts. As I said, it enables software implementation. It can run on existing smartphones. No additional hardware is required. And of course, low cost. I'm going to show a demo on a smartphone. This is a G8 of LG smartphone. The power is about 2 to 4 watts, 30 frames per second, up to 150 million rays per second. And you will see there's a counter on the screen to showing the rays of second, the count. The amount of rays per watt is very high. We have about 50 million of rays per watt. If you compare it with the big hardware ray tracing accelerators, this is completely in a different level. Okay, we're using about 1 ray per pixel in average, but for soft shadows, ambient occlusion and things like this, we're using 16 rays per second, per pixel, sorry, per pixel. The scene that you are going to see has 150 polygons. And we're going to see the functions of skin animation, mirror reflections, glossy reflections, hard shadows, and soft shadows. Okay, so on the left side, this is the counter, ray counter. We divide it into reflection rays and shadow rays. Now, first we see a shadow. This is a ray trace shadow. This is hard shadow. Now, you will see the shadow becomes a soft shadow. This is a soft shadow. This can be done only in ray tracing, soft shadow. And hard and soft. Now we're going to see a non-planar shadow on the character face. You see this is a non-planar shadow. Now the character is going to mirror. This is the mirror. This is the character in the mirror. Okay, here it is. Now you will see it becomes glossy. Different levels of glossiness, but it's glossy. You see that the inside, the picture inside is more glossy. Okay, so this is the demo. Okay. I would like to show the feature table that we have on mobile. On high-end GPUs, we have much more features, but on mobile, we have skin animation, we have hard shadow, we have soft shadow, we've seen it just now, mirror reflections and glossy reflections. Ambient occlusion is going to be, dynamic ambient occlusion is going to be ready in Q4 of this year, global illumination Q4 of this year, and refraction Q1 next year. Now the architecture of LocalRay, there are two components. The first component is for the developer. This enables game engine, LocalRay plugged in. Today we have it plugged into Unity. We are going to have it to other game engines as well. And the second component is on the device, LocalRay, which is, you see the second one here, and it's the component, the real-time component, which is working with Vulkan or OpenGL, and is working with a GPU, of course, and with a mobile. Now, we are ready for the Vulkan extension. We are going, this is the same architecture, but instead of have a runtime component, we are going to have a built-in LocalRay extension to Vulkan. That's it. Questions?
Hi, Reuven. That was really interesting. Thank you. Thanks so much. There is one question I see here. Hold on. Can LocalRay also be used on typical consumer PCs and Macs?
Yes. On Max is another engine. Max 3D, he means. First of all, it can be used on PCs. The first demo that I showed you, the New York Spider-Man, is done on a PC. The last demo is done on a mobile. So it can work on any GPU, on PC, on laptop, on tablet, and on smartphone.
Okay, wonderful, great, thank you. Okay, we've got some questions coming in. Does LocalRay have support for DXR?
Yes. On PC, it supports DXR. On mobile, it supports Vulkan.
Okay. At what resolution was the demo running?
Excuse me?
Oh, there's another question. At what resolution was the demo running?
It's a 1080.
Okay.
It's a high resolution.
Yep.
But we also have 4K. But this is of course slower.
Right.
This one was on a mobile, and it was 30 FPS in full resolution.
Okay. That was the extent of the question. I don't know if they had a follow-on, but there was another question as well. How does it work with Unity? Does it integrate into existing render pipelines? Do we need custom shaders?
No, you just need Unity. It's plugged into Unity, invisible for the user. You just work with Unity. And it appears as it has a button, and it's written Adshir. It's like working with different material, and it's built into Unity. And we're going to do the same for other machines, for other engines, game engines, like Unreal.
Okay, and when is, do you have a time for that?
If I have what?
When is Unreal going to be available?
For Unreal. It's going to happen next year.
Okay.
It's about Q1, Q2 next year.
1 Q, is that what you said? First quarter?
Yes, first Q.
Okay.
First quarter. Yes.
Great. I don't see any other questions. I think we're good. So thank you, Reuven. Thank you so much. You're calling in from Tel Aviv, correct?
Right.
Yes. So it's thank you for that. It's got to be getting pretty late there now.
Yeah, right. It's about 11 p.m.
Yeah. So thank you.
There's a nice moon in the window.
Oh, that's good.
Okay. Thank you very much.
Well, thank you. Thank you so much.